Welcome, welcome, welcome back, Gen Chem 1. Let's do this. I love it. We are going to do another type of reaction in our Unit 3 reactions. Remember the first half of our Unit 3, we're doing moles and mole calculations, and in the second half of our Unit 3, we are going to try and classify those reactions. So remember, each time we picture a reaction, it's like a whole story. And so the first half was all the calculations and the numbers with that story. And now the second half, we're adding all kinds of detail and definitions to that story. So it's pretty exciting. We're going to tackle and just start right where we left off in the last two videos where we looked at our redox reactions, and we kind of had a running list going on here where we start each one of our reactions by writing that whole thing out, and then we take a second and we balance it, and then we added a third piece in the last couple videos that we're going to add those oxidation numbers. So let's go through our process. And then we're going to add to that in this video. We're going to add another type of reaction. So let's just start with our process. Now, you might want to hit pause. What you're going to need in this video is your common anion sheet, because of course, we're going from names and everything in here. I'm doing that on purpose. And then we're also going to need what's called the activity series. Now, I posted on your Blackboard, right above where the videos start, you should have a little tab that says handouts. And you've got about 4 or 5 handouts in there. Some of those are from class before spring break, and just in case you don't have those with you, I posted those. So go ahead and print those out. You're going to need the one that's labeled activity series. All right, let's start. So let's take our copper sulfate. All right, what's missing right away from this name is, which copper do we use? Let's go ahead and do the copper 2 sulfate for this one. All right, let's take copper. And then why is it important that we have the 2? Well, otherwise we don't know what our formula is. We can't possibly draw that. All right, then our sulfate, when we look at the common anion sheet, we've got a -2 on there. Okay, perfect. And then it reacts with zinc. All right, that looks like just elemental zinc. Perfect. And then we're going to form zinc sulfate. All right, let's check our common anion sheet. What are our charges? Sulfate is -2. What is our zinc? That is a +2. And then we form copper. Looks like elemental copper. Okay, well, we know from the last 2 videos just on I can't talk tonight, inspection, that this is not a combination or a decomposition. How do I know? We've got more than one reactant and more than one product. So we're getting a little bit sassier, a little bit more complicated. Let's follow our process though. Let's write down our oxidation numbers. We've got a 0 for our elemental copper and our elemental zinc. And then remember, we take it one step further and we check what's inside our common anions as well. So it's just good practice. They may or may not change, but it's good practice. All right, we start with our most electronegative. That's our oxygen. That's a -2. And then we need that whole thing to add up to a -2. That's what that is. So our sulfur has to be, that's a little bit too fluffy to read, a +6. Let's double check the other one. That sulfate stayed together, so it's likely going to be the same. Oxygen is a -2. And it is, and that's a +6 for sulfur. All right, so let's just tackle the first one. Is this a redox reaction? It is. Look at your oxidation numbers are changing. So let's spell out those half reactions. All right, we've got copper on this side, copper on this side, and our copper is going from a +2 to a 0. I love it. In order to go from that +2 to a 0, did copper gain or lose electrons? It had to gain electrons to go from +2 to 0. And then what's the other one that changes? It's our zinc. We go from our zinc at 0 to a zinc at +2. And in order to do that, we had to lose electrons. Okay, perfect. Now these are our elements or our species that are involved in the redox. Now our sulfur and our oxygen didn't actually change in that sulfate. Sometimes that is called a spectator ion. We'll see that in our double displacement even more. It's possible to have things in your reaction that are not changing oxidation number. That is our spectator ion. And then our two that are changing, in this case, let's look at that reaction. It's almost like the copper and the zinc change places. It's almost like we just change partners there. And in fact, if you look at it, copper is bonded on this side. Okay, copper, we need another color here. Copper here is bonded. And if we look at it over here, it's in its elemental form. And then our zinc has just switched. So our zinc is going from its elemental form to bonded. All right, so this type of reaction is a redox reaction. It is called a single displacement. And why? Because you are literally displacing one of your elements for another one. Your copper and your zinc are literally switching places. Okay, now why? I mean, what would be the driving force for this? Like why would that even happen? Well, it turns out that these reactions are the original batteries. They're the original redox electricity producing reactions, and then we've seen them in all kinds of things after that. In fact, what we're looking at right now is the original copper top battery formula, one of the original battery redox reactions, and they're all single displacement. They have been around forever. Biological systems use them to get energy. I mean, they literally are everywhere. For us in electricity, studying that area, they've been around for 150 years. They've been known. So there is literally, these are up to Mother Nature, which elements displace which elements. But the good news is because we've been studying them for 150 years, I mean, go figure, they produce electricity, so they've been a hot topic. Get it? Don't you miss my jokes, y'all, in person? They literally have been studied for so long that strength and who is displacing who is really known. And in fact, it's known so well, it is put into an activity series. So I'm going to show you how to read that. So copper and zinc, because this is one of the original batteries, this particular reaction has been known for over 100 years, if not closer to 150 years. So obviously there is a strength between copper and zinc. One of them is stronger than the other, and that is the kind of the driving force on why one of those displaces the other. So since these have been known and they are in a table, you can test these, but this is where for this type of reaction, we will use the activity series. We will let Mother Nature tell us which ones are going to displace the others. So how do we read it? If you grab your activity series, like I said, I've got it posted for you online. They almost always have gold on the bottom and lithium on the top. Now you want to be careful if you just Google your own, because you'll find all kinds of activity series, but what we're aiming for is in Chem 2, we're going to look at electrochemistry, and we're going to look at standard reduction potentials, and those are written the opposite. So you want to make sure you're looking at a table that has gold on the bottom and lithium on the top, and we're going to read it for strength this way. Okay, now what do we care about strength? Well, I'm going to give you a little tip here. Strongest ends up bonded. All right, so if we're looking at, okay, how do we know and what do we compare? Well, we already spelled out our half cell. That's our copper and our zinc. So those are the two you're going to compare on the table. And if we grab the activity series and we look at it, we're going to notice that copper is kind of down here. Oh, that's really crappy writing, isn't it? We're going to notice that copper is down here. And then let's find zinc, and we're going to find zinc is kind of towards the middle. All right, so that means zinc is higher up on the table. Zinc wins. So if we go back to our original equation and we look at it, what it means is that in nature, if you mix your copper sulfate and zinc, it will react this way and your zinc will end up bonded. Okay, look at that. We wrote that the right way. This is how your battery will give you a flow of electrons. And now, you know, batteries like Duracell go in one direction. So this is a full battery. This is an empty battery. Once you form those products, you're done. Your battery is dead because zinc always wins over copper and your reaction is done. Now, for some of these, you can go backwards, but how do you go backwards? Well, this time you have to apply a charge. Okay, now this particular one I don't think goes backwards, but that's how we have more modern terms, rechargeable batteries. And what do you have to do to recharge your battery? You apply a current. That's how you get your battery to go backwards. So the activity series really isn't up to you. It's published. It's something you're going to put on your cheat sheet, and we're going to use it to predict these reactions. We're going to use it to write our products. We're going to use it to figure out what happens, and we're going to use it to figure out if a reaction would even happen. You know, there's nothing worse than mixing up what you think is a battery and it's dead already. That's because you just didn't read your table the right way. So we'll take all of this and let's apply it a couple times. All right, let's scroll down and let's do another one. I love it. I did actually put an activity series link on here if you want one, but like I said, I also gave you all of those handouts on your Blackboard. All right, so what kind of questions are you going to really run into for these single displacements? Well, what if we give you nickel nitrate and it reacts with lead and it forms lead nitrate and nickel? Or does it? So let's actually figure out if this reaction, what it's going to produce and if it would even happen. So let's start with our nickel nitrate. All right, that's from our common anion sheet. Our nitrate charge is what? A -1. And our nickel is a +2. That oxidation number was given. For funsies, let's go ahead and do the oxidation numbers for the nitrate. Whoa, what did I just do? Okay, so our oxygen, we start there, -2. And then what does nitrogen have to be? So we've got a -6 with that oxygen, but we have to add up to a -1. So that means your nitrogen has to be a +5. Okay, is that an option for nitrogen? It is. All right, and then we're going to react it with elemental lead. And then we're going to make lead 2 nitrate. And our nitrate is a -1. So hang on a second. We've got some fixing to do here. Don't we need 2 of them on both sides? I love it. All right, so let's pause for a second. We're not quite done writing this out, but let's see if we can predict what else we're making in this reaction. So out of this reactant side, what is changing already in our oxidation numbers? Because remember, these are redox. All of our single displacement reactions are redox. So we always have 2 partners. And let's look at this first partner, lead. Our lead is going from 0 to +2. Okay, awesome. So that means it is losing electrons. Okay, and then our nickel. We didn't write nickel yet, but our nitrate, is our nitrate changing? No. So that's got to be a spectator ion. Well, we have to have something else change. And we saw in that last example that it's almost like our two metals change. They switch partners. So the other partner has to be your nickel. It's the only thing left. And then nickel is going to change from +2. What is it going to change into? Well, we just switch partners, so it's going to end up by itself. I'm sure you can make all kinds of bad dating jokes right now. But your strongest one ends up bonded. So, and then we're going to gain electrons to do that. All right, so these two are the two that are switching places, and those are the two that you compare on your activity series. So remember, we're going from gold to lithium. So let's find lead. That's kind of here. And then let's find nickel. And if I look at my table, I kind of see nickel is just a little bit above lead. So that means nickel wins. Okay, awesome. So did we write this reaction the right way or no? So in fact, let's erase that arrow. What arrow would we put into this reaction if we need this reaction to work? Would we go in the lab and mix our nickel nitrate and our lead? No. Remember, nickel nitrate your nickel has to end up bonded. So that has to be our product. So in fact, this reaction has to go in that direction. We did write it wrong. Right? It actually would happen only if you mixed lead nitrate and nickel. That's what the activity series tells you. It tells you which two are going to switch places, and you compare those on your activity series. And if you want to follow a pattern, I like to write it like this. A lot of textbooks write them this way. So how do you know which two to compare? You're always comparing the single, and you're comparing the cation, or the first one. And then what do you end up with? You're going to see if your C ends up bonded and your A ends up all alone. So that is the general structure for our single displacement. So when you take this test or you do this homework, you need the activity series for this type of reaction. Now the activity series only works for single displacement reactions. That's it. Okay. Awesome. We're on a roll. Let's do another one. You can tell I had fun writing these. Calcium phosphate reacts with potassium to form potassium phosphate and calcium. Or does it? All right, let's see if we can figure this out. Calcium phosphate, holy crap, grab your common anions. Let's write that out. Calcium, what's our charge? +2. Phosphate, oh, of course, right? Our worst nightmare, that's a -3. So how are we going to make that work? We're going to need 3 calciums and 2 phosphates. And we're going to react that with potassium. And we're going to form, or are we, potassium phosphate. All right, how are we going to draw that? Phosphate, remember, is a -3. We're going to need 3 potassiums and calcium. All right, let's identify what is switching places and what is changing in our redox. And then, of course, for fun, couldn't we try to balance this reaction? That might be something you want to try, and you might want to balance it. All right, here's your calcium is the one out front, and your potassium, that kind of follows our normal single displacement. Okay, so those two are the two that are changing, and they're the two that are switching places. So let's spell that out really quick. Our calcium and our potassium. And our calcium is going from a +2, and our potassium from a 0. We are going from +2 to 0, and a 0 to a +1. Okay, I love it. So that means that potassium is going to give away an electron, and calcium is going to take it. Let's check our sheet then. All right, now we know the two partners. These two partners are the two that change in your redox, and those are the two that switch partners, or do they? So let's check our activity series. Okay, we go from gold to lithium. Wow, if I don't get that angle right, that just writes so fluffy, doesn't it? All right, we're going to go from gold to lithium. Strongest one wins. Strongest one ends up bonded. So calcium, sweet Jesus, that's way up here. Okay. Oh, but hold the phone. Holy crap. If calcium is up here, well, shoot, potassium's even higher. All right, so that means potassium wins. Winner. Winner, winner, chicken dinner. Okay, so that means that our potassium ends up bonded. And in fact, it does. In the way that we wrote that, our potassium ends up bonded. Oh, I think I highlighted a little too sassy, and then it's hard to read the answer. So we did write the arrow the right way. This is awesome. This reaction would work, and it would go in that direction. And now for funsies, you should try to balance that reaction. That would be a good practice. Okay, I love it. I hope we're getting the hang of it. Let's do another one. Or not. Okay, so I think we have some homework that's out there for these. And then we also have some other examples coming up that are going to be our double displacement reaction. So what do you need to try in these single displacement reactions? You need to make sure that you can read your activity series. And make sure you know which partners are switching places. So you're going to follow that these